There is an important comment to make about intrinsic meaning of splitting fields. Remember that after learning to attach a single already existing element, we generalize to attaching an abstract element by using the quotient construction. Exactly the same way, instead of repeatedly attaching pre-existing complex roots of a polynomial to split that polynomial, I can repeatedly attach abstract roots to achieve the same effect. At each stage of adjoining, I have to take care to go modulo a polynomial that is irreducible over the already constructed field. This is because I always want to have a field. Try to work this out here and write down an abstract version of this splitting field E. X cube minus 2 is irreducible in Qx. So, when I create a root of this polynomial by going modulo it, I get this field E1. I have given the name T1 to the variable and the created root is the congruence class of T1. E1 contains Q as constants. So, x cube minus 2 continues to live in E1x. And here, by construction, it has x minus the new root as a factor. So far, there is nothing new. Now, let's look at the remaining quadratic factor. I claim that it is irreducible over E1. Why? Remember a concrete model we have for E1. E1 is isomorphic to Q adjoined with the real cube root of 2, and that does not contain the two non-real roots. So the isomorphic field E1 does not have any roots of this quadratic factor. Then I can go modulo that factor and get a still bigger field E2. Again, I have used a new variable name T2 so that we can keep talking about the original polynomial in variable x. Now, over this new field E2, the quadratic polynomial factors and I can stop. I have also written down an explicit factoring using the fact that the sum of roots can be read off from the coefficient of x square, which is 0. This abstractly constructed field E2 is isomorphic to the earlier concrete splitting field E inside complex numbers. You should check this as an important exercise. It will help you understand this procedure better. Even more importantly, we want to apply the same logic to any polynomial g of x, whether irreducible or not, over any field f to construct an abstract splitting field of that polynomial. So pause and try to formulate a statement on your own. I claim that given any non-constant polynomial g of x over any field f, there is a minimal field extension E of f such that g of x factors as a product of linear factors in Ex. This just means that, speaking informally, g has all its roots in E, and minimality means that no smaller field will suffice. If I have a large field containing all roots, then minimality is easy by attaching just the roots, like we did in the concrete splitting field. But in fact, our construction will stop at the right object, and we proceed exactly as we did for x cube minus 2. But first, we factor g of x into irreducibles, because going modulo a reducible polynomial will not even give a domain, and I always want to have a field. After going modulo an irreducible factor of g, I have a bigger field in which g has a new root. Now I factor g again over this larger field. If there is any irreducible factor of degree greater than 1, I go modulo that again to acquire yet another root. Then I inspect g again and continue as long as necessary. Every time I am using a new t as the next variable to keep the notation straight and so that I can keep talking about g of x. There is a lot to unpack here. So let's start with two basic questions. Why and when does this procedure stop? And how is this procedure related to attaching all pre-existing roots? Let's say from an algebraically closed field containing f, like we used complex numbers earlier for a rational polynomial. The answers are not hard, so take the time to figure them out. Let's see the answers. At each step, I attach a new root of G to my current field EI. G can have at most as many distinct roots as its degree. Call it n. After I have n minus 1 linear factors, the remaining part is automatically linear. So the process terminates in at most n minus 1 steps. The last field Ek I get is the E I wanted. The number of steps k can really vary. At one extreme, I may need the maximum possible n minus 1 steps. But the following may happen. At any given stage I, as a consequence of attaching one root of an irreducible factor hi, the factoring of g over ei may break up more than acquiring just one extra linear factor. Over the new field ei plus 1, hi or some other irreducible factors may acquire more roots, or they may factor further without acquiring roots. So there are a lot of possibilities. At the other extreme, the process may terminate in a single step. Attaching just one root of g may lead to all other roots automatically being included. For example, you should show that this always happens for any irreducible polynomial over a finite field. Next, after I have constructed E, I have the full set of roots of G concretely available inside E. So I can attach all these concrete roots, namely T1 bar, T2 bar, etc., and maybe others that got included along the way, to F inside E. You should observe that this concrete adjoining gives back all of E. So E is minimal because all roots of the polynomial G are needed to split it into linear factors. In light of this, we can also regard our abstract construction after the fact as a concrete construction of a splitting field. This may seem like a cheating answer to my second question, because I want to relate this construction to a given concrete splitting field. This objection is related to the uniqueness question about the end result E of our construction. I have to analyze uniqueness because I am making choices along the way. We will give an answer, but for the moment, let's assume that the splitting field E is unique up to isomorphism and step back to see what tools went into constructing E. Technically, the answer is very few. We use the quotient construction, the fact that fx is a PID because of long division, and that going modulo an irreducible polynomial gives me a field. That's it. And for uniqueness, you only need substitution principle and the isomorphism theorem. Out of this basic toolkit, we magically created a world where we can study the intrinsic behavior of the totality of all roots of a polynomial. This construction is worth meditating on, especially when illuminated by a variety of examples. So let's see it in action. The first exercise is optional for this course. I have given a formal definition of a splitting field which applies to both concrete and abstract versions. I have stated the uniqueness result and sketched a proof. With the hint, it is not very hard, so I encourage you to try it.